Hello students, let's try to wrap up week 4 with 3 problems. We will go through the numerical substitutions to a lot of the equations that we had derived, just so that you also get a hang on how to solve real world problems with transmission lines, right? So we are going to put some numbers to the variables and phasors that we had derived. So the first problem statement is in front of you. We say that a voltage wave at 1 gigahertz is traveling on a transmission line in the positive x direction. They have given us the primary constants for the transmission line, the R, L, G and C values. The moment you see this, it should be clear to you that you can estimate two of the main line parameters, which is the characteristic impedance as well as the propagation constant gamma, right? And since R and G are non-zero values, you expect to see complex numbers for both of them. It says that the wave has 30-degree phase at t equals 0 and x equals 0. This is to say that in the polar form for the voltage, the phase of the voltage is 30 degrees at the chosen reference of x equals 0 and t equals 0. So the first bullet says calculate the attenuation constant in nepers per meter and dB per meter, right? So I chose this question specifically so that you are clear as to how to go back and forth between both these units for attenuation, right? So we have propagation constant gamma, which was square root of R plus j omega L times G plus j omega C. Okay. So we simply substitute. So R is half ohm per meter. Remember, R, L, G and C are the distributed quantities, right? So you can notice that the quantities given are all per unit length, right? So we don't have to really do much more than simply substitute the numbers given to us. So I have 0.5 plus j omega is 2 pi times 1 gigahertz is 10 to the 9 hertz or 10 to the 9 inverse second omega times L, L being 0.2 microhenry. So that's 10 to the minus 6 right, Henry per meter. So we can have this multiplied by G plus J omega C, which is 100 pico, 100 into 10 to the minus 12. Okay, remember all of this is under square root. Okay, so I have a complex number R plus j omega multiplied by another complex number G plus j omega C. Okay, so let's see how these numbers pan out. So I have half plus, so I have 10 to the 9, 10 to the minus 6, when I multiply that's 10 to the 3. So you can also try to do the calculations along with me. .1 plus j So 10 to the 9 and 10 to the minus 12, that's 10 to the minus 3. Right. So again, as engineers, it's very important that we are good at making some quick assessments, right, in terms of large numbers and small numbers. So if I were to expand this, so of course there is one very large term, 400 pi times j, right? It's a very large imaginary quantity. So omega L of course fits the bill to be much greater than R, right? However, omega C we cannot quite make that comment, right? So we cannot go into the low loss approximation. So nevertheless, we will try to expand this, and we will keep in mind that we can always simplify when we have large numbers in comparison to small numbers. Okay. And j times j is minus 1, so I have minus pi squared 80 pi squared. This is the real part, and then I have the imaginary part. Right, so I am just multiplying out the two complex numbers. So now of course I can make some approximations. I can neglect 0.05 in comparison to 80 pi squared, right? Pi squared is roughly 10, so that's around 800, right? So in comparison to 800, 0.05 is extremely small, so there's no point in carrying that along with us. Similarly, I would say that even 0.1 pi in comparison to 40 pi is a rather small number, right? So we can just say that this is approximately equal to minus 80 pi squared plus j 40 pi. Right? Okay. So now I can further do, if I were to do some back of the envelope calculation to get some approximations, you can certainly type this into a scientific calculator and get the right answer right away. But I feel like I can go a little further in terms of just assessing this. So I'm going to take a minus 1, that will become a j, and then if I were to take 80 pi square completely outside, I would essentially get this is all rough, right? So pi squared is close to 10, so I have 800, and 800, the square root of 800 is 20 square root of 2, and then I have 1 minus j by 2 pi. Whole to the power of half. Okay, if I were to use the 1 plus x bar k as 1 plus kx approximation, I can actually get this close to 1 minus j by 4 pi. Okay, so if you remembered, we said gamma was alpha plus j beta. So if we were to look at alpha from this equation, that would come from multiplying the 20 root 2 j with the j by 4 pi, right? So that's essentially plus okay. This is all approximate values. You can actually use a calculator and see how close our approximations are. This is perhaps a useful skill, right, to be able to use a lot of the mathematical approximations that were taught to you during the derivations, right, even when you are given real numbers. Okay, and beta is again 20 square root of 2. Okay, so beta is in radians per meter. Okay, so square root of 2 is around 1.41, and when I multiply that by 20, I perhaps get about 28.2. Okay, so remember, even when you are writing your quizzes and finals, units are highly important, right? So beta has units of radians per meter. So this alpha 5 square root of 2 by pi this I can probably punch into my regular calculator, and it turns out to be around 2.23, and the units is nepers per meter. Okay, so the units of alpha as is nepers per meter. So when I substitute R, L, G and C into the expression for the propagation constant gamma, I actually get a real term, right, which is alpha, and the units of it is nepers per meter. Now if I would like to go to dBs per meter, that is where I need to convert this number, right. So dB per meter is a unit that is often used when you are looking at powers, right, powers at different points along the transmission line. So you would like to know how much power loss you've had, right, rather than knowing this alpha. You probably want to know that if I launched some power at the starting of the transmission line, due to the transmission line losses, how much power have I lost, right. So power scales as the square of the voltage, right. So in order to get the loss in dBs per meter, I have to do 20 log to the base 10 of the voltage at say x equals 0 to the voltage at x equals 1, right. So all you have to do is 20 log to the base 10 of this. Essentially turns out to be e to the alpha, right. You can go back to the discussion on alpha in the prior lectures this week, and you will notice that this turns out to be just e to the alpha. So we know alpha here, right. So, all we have to do is just take 20 log to the base 10 of e to the alpha, which is using the mathematical rule for logarithms of exponential numbers. We can just write this as 20 times alpha log e to the base 10, right. So, this turns out to be 20 into 2.23 nepers per meter divided by natural log of 10. Okay. Natural log of 10 is something that I remember, but it's around 2.303 and it's very close to the alpha value that we have gotten. So, my hunch is that the loss in dB per meter is going to be very close to 20 dBs per meter, right. So, the exact value turns out to be okay. So, we have concluded the first bullet, solving for the first bullet. So, the loss or the attenuation constant in nepers per meter is 2.23 nepers per meter, and in dB per meter it is 19.36 dBs per meter, right. In some very simple sense, let us assume 20 dBs per meter, right, for conversation. What this means is the power level, right, of the signal that is being transmitted along this transmission line, right, over a 1 meter distance along this transmission line, we have nearly lost 99% of the power, right. So, what is remaining at the end is about only 1%, right. So, 20 dBs, remember, is a factor of 100. So, if I started with about 1 watt, I only am left with 10 milliwatts at the end of the transmission line. So, this is probably a fairly lossy transmission line for 1 gigahertz. If you were asked where exactly is this loss coming from, is it perhaps from R or G, could you take a guess at this time? So, I have given you a couple of seconds. Remember that when we substituted gamma is equal to square root of r plus j omega L times g plus j omega c, r was substantially smaller than j omega L, right, whereas g was not much smaller than j omega c. So, you can actually say that the losses through the dielectric is perhaps the key reason for the loss that we are calculating here, right. In fact, you can even go to the extent of saying r is equal to 0 and estimating gamma, you may find that your alpha values do not change by a lot, right. All right. So, let us go to the second bullet. Now, if the voltage of the forward travelling wave at t equals 0 and x equals 0 is 8.66 volts, find the voltage at x equals 1 meter at time equals 100 nanoseconds. What is the peak voltage at x equals 1 meter? Okay. So, if you remember, we had written voltage V as a function of t is essentially the real part of the V plus phasor. Remember, there is only one wave here, right? There is only one wave going in the positive x direction. So we had e to the minus alpha x, e to the j omega t minus beta x, right. So now some things that they have given us is the angle for V plus phasor is 30 degrees at x equals 0 and t equals 0, right. So it seems like the phase is not quite 0 degrees when you started observing. So there is some phase to this, right. Why did I say that this is only the phase of V plus phasor? Because when I substitute x equals 0 and t equals 0, the phase contribution coming from this term e to the j omega t minus beta x is 0, right. So there is no phase contribution coming from there at the chosen initial condition. So all the phase that is coming, right, at t equals 0 and x equals 0 should be from the phase of the phasor V plus. Okay. So if I were to say V of 0 comma 0 is real part of V plus magnitude e to the j angle of V plus, and x is 0 and t is 0. So e to the minus alpha x is just 1 and e to the j omega t minus beta x is also 1. So this is quite simply just the magnitude times cosine of and this has been observed to be 8.66 volts, right. So they have measured the voltage on this transmission line at x equals 0 and t equals 0, and they find it to be 8.66 volts, and they also know that it is got a phase of 30 degrees. So we can actually say that I can get the magnitude of V plus by cosine of 30 degrees. This happens to be 10 volts. Okay, cosine of 30 degrees is square root of 3 by 2, which happens to be 0.866. So this is roughly 10 volts. So now you know what the magnitude of V plus phasor is, and the next part of the question should be fairly straightforward. Now you should essentially be able to tell what the voltage is at any x comma t. If this was the only wave that was traveling along this transmission line, and if this transmission line is never ending and there is no loads or sources for reflections, you essentially know the voltage on this transmission line at any x and any t, because you just know this expression, right. Okay. So we are going to say that V of x equals 1 meter and t equals 100 nanoseconds. Okay. So all I have to do is, so the real part of this can simply be written as modulus of v plus e to the minus alpha x cosine of, let's call this an initial phase phi plus omega t minus beta x. Okay, so let's calculate omega t. So this is 1 gigahertz, so 2 pi times 10 to the power 9 hertz multiplied by 100 nanoseconds, that is 10 to the minus 9 seconds. So this is about 200 pi. That's convenient, right? Because it's a multiple of 2 pi, so it's essentially not doing anything. Let's see what about beta x. So beta was 28.2 radians per meter multiplied by 1 meter. So that is 28.2 radians. Okay, we can try to bring everything to radians, that may be useful. So phi is 30 degrees, which in radians is pi divided by 6. Pi is 180 degrees by 6 gives us 30. So you can say that this is 10 volts. E to the minus alpha was 2.23 nepers per meter multiplied by x, which is 1 meter, is 2.23. Cosine of pi by 6 plus omega t is 200 pi. So I can probably not worry about that, minus 28.2. Okay, so please be careful when you are punching these numbers in the calculator, whether you are in degrees or in radians, right? And make sure that you convert all of them to the same units, right? So this happens to be minus 0.8887 volts. Okay, you can double check. So 28.2 pi radians is about 3.14, right? So 28.2 you can sort of roughly estimate about 9 pi, right? 9 times pi would bring you close to 28.2, right? So you can also ensure that the signs that you're getting, everything can be checked, okay? And then if I were to ask you what is the peak voltage at x equals 1 meter, remember that this cosine term is going to oscillate between plus and minus 1, right? So x is fixed, phi is fixed, omega t is going to keep oscillating between 0 to 2 pi, right. So, taking the cos value from -1 to +1. So, the peak voltage would be when the cosine term becomes 1, right. So, if I wanted to just know the V peak at 1 meter and 100 nanoseconds, all I have to do is just 10 e to the minus 2.23, right, because the cosine term is just 1 and that happens to be 1.075 volts. Okay. So, hopefully you have gotten a basic idea of how to calculate your alphas, betas given the omega and the line parameters of RL, G and C. Okay.